Forceful about that. The title of his paper is Improving Ride Quality Using Track Geometry Waveform Analysis. His background is a PhD in civil engineering from UMass Amherst. Steve Krisma has worked in the rail industry for 40 years in both track and vehicle engineering, specializing in vehicle-track interaction for freight and high-speed operations. And that was all with Amtrak, I guess. Mostly, yes. Okay, so we're really honored to have you, Steve. Please step up.
Thank you. Thanks so much. The topic today, waveform analysis. Now, if I assume many of you have ridden Amtrak, and so maybe you understand the sense of urgency that some of us felt in improving the ride quality. How do you do that, given this present situation? Well, my colleagues here and I came up with an approach, submitted for your approval, that when you try to solve a ride quality problem, you're trying to solve a vehicle-track interaction problem, aren't you? So if you look at it in those terms, you might want to look at both the track and the vehicle's response to the track with its geometry irregularities in terms of the waveform, right? Well, so we look at the track as a starting point and look at the static waveform, or the standing waves, if you want to characterize it that way, and compare that to the dynamic waveform of the vehicle in response, so the car body, accelerations, dynamic motion, and so on. The problem that we came up against was, though, that typically we're looking at track geometry from the point of view of safety and deviations that would threaten safety, but when you look at ride quality, or the track geometry deviations that drive ride quality, they're often much smaller and harder to see. They're not on our radar very often. So what we needed was a tool to bring them out, right? And then also to then go one step further and then look at the vehicle's response to the track geometry and look at the car body accelerations, look at that waveform and compare the two. So that when we say waveform analysis, we're talking about both the track geometry waveform and the car body dynamic response waveform. So that's in the direction we're going here. And as we say, the last bullet point, something we struggle with. How do you return the track to its design position? Because that's the ultimate goal, isn't it? And I know colleagues back here, back in the day of British Rail Research, they were looking at that. We watched them looking at that and tried to draw from their experience, and have done so successfully, I think, although it's in progress. But so waveform analysis can also help in that regard to guide us to what is a better solution. How do we return the track to its design position and get the ultimate improvement in ride quality? So as we know, the track roughness waveform, when you look at the space curve, let's say, from a track recording car, geometry measurement car, has an appearance, as you see on the top, of random chaotic waveform. But as we know from Fourier's analysis, you can decompose that into rather simple sinusoidal waves of various wavelengths and different amplitudes. So we can use that same kind of process to go from the top line to understand, well, what is there? Maybe there's a specific or a certain wavelength that is driving the rough ride quality. Well, what is that wavelength and what is its amplitude? Right? That's what we're after here. So let's use that an example, an actual space curve. This is profile now, and the Y scale is a bit exaggerated, so you can see it's not really that rough. It may appear just because of the scale that I chose. But this was a track location that caused repeated ride quality exceedances for the Acela train set, and we couldn't figure out why. Because if you look at the scale, the Y scale is very large, right? So compared to the length, that's actually not that bad of a track. A little rougher on the left side than the right side, but really not approaching a safety issue at all. But the vehicle took exception to that and repeatedly had a vertical acceleration exceedance every time we go over the track. So what is it about that track? We didn't see anything, at the maintenance level, certainly. But there is something inside hiding in there, and when we did the analysis, we found these sinusoidal shapes that had this ramping up effect, as you see on the left, and plus or minus half an inch. Doesn't sound like very much, right? And that's over something like 300 feet. oh my goodness, that's, you know, we're just not used to looking at that as anything, certainly not as a safety issue, but from a ride quality issue, it was. So we had to kind of retune how we thought of things, right? This almost appeared to us at first as, well, this is just ripples on the top of the ocean, you know, this is so such a small, but the vehicle, of course, did not see it that way. So we had to sort of speak the language of vehicle track interaction and understand what the vehicle was, what the vehicle and track were saying to each other. We had to learn to speak the language. So this waveform analysis allows us to get into this waveform, such as the space curve, and see what's hiding in there and disrupting things. All right, so that is an example of one of the problems that we started to detect, and once we started looking for them, we found them all over the place that look like that. Now, we need that's okay, that's not bad, you know, we're on our way here, but it's not really the most efficient way to look. So what we did was we used what you see here, that was the graph we just saw, but we said, well, that's one wavelength, 300 feet, that is a problem, but we know that if you look at the example waveform, it has all kind of wavelengths in it, right? Short to long and everything in between. And it's not just the 300-foot wavelength that's driving it, it's, as we did the data transformation into this is the same data, we just transformed it into this heat plot, as we call it, to then tell us, well, what is the range of wavelengths or amplitudes, I'm sorry, the wavelengths that have accentuated amplitudes, the track roughness. And it exists over not just 300 feet, but plus and minus of that, right? So the actual track roughness comes from wavelengths ranging from about 200 to 400 feet, with 300 feet just being the medium, right? This then tells us what we're up against. We have to smooth track over that entire roughness wavelength, where it has elevated amplitude, rough track roughness. So understand what we did here now. We took this data, the space curve, and we sort of went into the page by using this analysis called convolution. Taking the original waveform, perform the convolution, which then gives you this heat plot, right? Sort of a three-dimensional quality now. So what we've done, we've flipped our perspective. Here we're sort of looking at the track along, we're standing to the track side, looking along the length of the track. But we want to go into this page to see the various wavelengths that are having high amplitude. So to do that, we flip this 90 degrees. Now we're looking down on the track from above. These three arrows point to the peaks that we're looking down from above. We've flipped our perspective now, right? And we're now looking three-dimensionally. So there gives the amplitude, so that's why we say it's a contour or a relief map, and your brain can sort of sense that or feel the shape contours. And now it becomes more intuitive what you're trying to solve. All right, so that then is what we do from the track data point of view to get the heat plot. We did the same thing for the vehicle response. It's a vehicle track interaction problem, right? So we did that also with regard to accelerometer data mounted in the car body. So once again, we have the same perspective now. We're looking down the track from above, and now these hotter colors are the car body coming to you and bouncing up and down. As it comes to you, it gets hotter. So that's what you're seeing in this case. So that is the dynamic response to the track geometry static waveform. And what it's telling us is, now these are the wavelengths of car body acceleration or dynamic motion. And we can tell certain things. Well, okay, we can see that it tends to follow a line, a certain wavelength that it wants to bounce at. But what that really is, bouncing at a resonant frequency of about 1 hertz. For this vehicle, that was the resonant bounce frequency. It wants to bounce at that. So that tells us what is going on with the track. That's the feedback. It's telling us we have to correct the profile. There's really not much else going on in other wavelengths. Here, just for reference, we say, well, if it was bouncing at 0.5 hertz, it would be up here. No, it tends to bounce right around the resonant bounce mode, which is not surprising. That's for vertical. Then if we look at the lateral acceleration data, we see a little bit different picture, because lateral ride quality and vertical can be quite different, right? So the lateral, once again, we do see activity right around 1 hertz, but we also see quite a bit of motion energy at lower frequencies. What does that tell us? Well, probably right here, the red zone is very likely a more of a pure lateral motion. But the slower frequency motion is very likely car body roll, because that does occur at lower frequencies, like at around half a hertz and lower. So right away we can tell, go back to what the track geometry feature likely is, that if this is more of a pure lateral alignment deviation, this is probably caused by more of a difference in cross level. As you go down the track and you sort of vary the cross level, you get that rocking motion, rolling motion in the vehicle, and giving a lateral component. So you can, again, go back to what it's showing you here, to the track geometry feature that you have to correct. All right, now here is everything together. So now we are solving vehicle track interaction. At the top, two graphs have to do with what the track is showing us. The bottom two is what the corresponding vehicle response is. And now we've got the total picture. We see, in the case over here, a cyclic deviation shown by here, but illuminated even better in the heat plot transformation. And it's telling us that, now I understand why I'm getting this cyclic repeated bounce of the car body, which is shown maybe better here again. It's the same data, but we just transform it, looking down now from above. And we see maybe something like 10 cycles before it dies away. So that comes to us from a cyclic deviation that we have to address. This, on the other hand, is different. This is more of a local spike, just a single deviation that drives this 2 or 3 cycles of motion, then it dies away. So the response is different. Here we just want to remove that if we can. Here we have to remove the deviations over a substantial length of track. Yes, I know there is some higher wavelength activity or amplitude up here, but it doesn't matter, because given the speed of the car, it doesn't really see that and it's not affected by that. Here at this mid-range, it is. It depends on the vehicle speed. All right, so I have a few examples of how we went then applied this. And in this case, this is a situation where you have a single isolated deviation in alignment in this case. And that is driving an awful lot of what we call ARMSITs, automated ride monitoring systems. So when the vehicle accelerometer has an exceedance, it sends a signal and it's mapped as to where that occurred. And I sort of blew up the X scale so it looks a little bit rougher than what it is, but there's some deviation or error in where this occurs, plus and minus. But the center of the cluster is right about where this is actually occurring. And so there's no cyclic thing to fix here. It's rather a go to this spot and fix that location. But then again, when there is a deviations over some length, here again you see it in the space curve, but it is better shown by the heat plot transformation. Here again now, this is not, these deviations are occurring in clusters. Little one here, bigger one here, here and here before it dies away. So in this case, we have to go in and actually correct this entire length, not just a spot. And the last example I'll give you is one where there is no real geometry deviation that's at fault. Here you can see we have an awful lot of lateral exceedances of the accelerometer, but if you look at the heat plot, you don't really see hardly any geometry irregularity of note, and the same is true of the space curve as well. But you're in a shallow curve, right? A very large radius curve where you enter here and spiral, and the full body is less than half a degree, so that's a very shallow curve. What happened was, in this case, the cause is wheel rail kineticity, because hunting can occur, as we know, it usually occurs, the lateral instability of the wheel rail, in tangent, straight track, but in this case it was in a shallow curve, because the wheel set moves to the outside rail somewhat, but not fully committed against the flange, right? So it's a little bit unstable. The contact point is right in the flange throat radius, not on the tread, not on the flange, but intermediate, so that's a high kineticity situation. The solution here would be grind the rail to relieve that, or move the contact point to a lower kineticity. Okay, so in other words, waveform analysis can be used to show that the problem is not track geometry, it's something else. So, this is the last heat plot I'll show you, but it's sort of I think our crowning achievement, because, as I say, we struggle with returning the track to its design position. Right? This isn't a curve, where before, all the before conditions, we could never really improve it. We'd send the tamper in every so often, maybe yearly, and incrementally, we wouldn't improve it. Sometimes we would actually make it a little worse. We decided to try to break out of that situation by using an improved alignment method, which worked. And that's shown here. You see that we had wavelength roughness out as high as 500 feet, but after this improved technique to remove this, it was all gone, right? And if you prefer, you could look at it on the space curve, alignment space curve. This is looking down the track from above up here. So we basically went from the blue to the red. It's almost like we took both ends and sort of stretched them out, lowering the amplitudes and stretching out the wavelengths well beyond 500 feet, well beyond where we care about, even for the highest speeds. So waveform analysis was able to show us how well we did, and in fact there were competing methods that we could use to try to get this improved situation, but waveform analysis showed us which of those was most successful at removing these deviations and putting the track back to its design geometry. So, with that said then, we'll wrap up by concluding that, as I mentioned, waveform analysis can reveal right quality problems that have gone undiagnosed, right? We just have no explanation. Because these deviations, geometry deviations, are often so small that it's hard to see. Waveform analysis enhances them, brings them out, so it makes it more obvious. And then we use that analysis to determine the needed action to improve right quality. What do we fix in the track? What track geometry feature do we need to focus on? Is it profile? Is it lateral alignment? Is it cross level? What's it going to be? And as I mentioned, the last thing there, it can guide us in terms of finding the track maintenance method that is most well suited to improve the situation. So that concludes the, I want to mention by acknowledgement, the software that we use to do this is Railway Doctor, which was developed by Mika Silvas from Finland and his associates, which was really helpful to us. We had no other method at the time, but you could use, of course, R or Python. There's other methods, but in this case, everything that you see was brought about by Rail Doctor. And that's all I had, but let me end with this slide, because to me it's a thing of beauty, and arrived at after many years of hard work.
Another great presentation. We're going to take you at the back there, just beside you, and we'll...
Keep talking, right? Steve.
So sorry, can you remind people who you are?
He did.
You did.
Mike Ford, University. You kept mentioning how it feels to ride. What exactly, as a user of Amtrak, what am I feeling over that 300 to 500 foot section? And is it more felt or more noticed, above 50 miles an hour, above 90 miles an hour, or is it at slower speeds?
Right. So all of what we're seeing here are at the upper end of, not the maximum speed necessarily, but let's say above 80, above 90 miles an hour. Yeah, typically, that's what we're looking for. Okay, when dynamics get exciting up that range, and that's when the amplitude does not have to be very big, but again, we're not seeing it. So unless we use something like this, we could very well miss it. But anyway, does that address what you said? Yeah, and we find these all over the place, like I said. Once we started looking for them, but now we have to once we can find them is one thing, but now we have to fix them. So that's sort of the next phase, to get better at repairing them, removing them.
Okay, Carl Ho from University of Massachusetts. Steve, thanks a lot. That was a really great presentation. One of the thoughts I had is I assumed that the velocity of the train within this stretch that you were showing us was pretty constant, but we know that the trains have different velocities of different zones, and the response of the train is really on a time basis, and the space curve, the analysis of the waveform, is on a distance basis.
Right.
So is there any thought of trying to do an analysis throughout the entire length of the line, and sort of adjusting the length basis to a time basis to see what kind of frequency content you have, because I think that would be something that would show up a lot more with respect to how the vehicle responds, and even different parts of the vehicle. I mean, you might be seeing that the locomotive responds one way, maybe the cars closest to the locomotive respond one way, but the cars farthest from the locomotive respond a different way.
Yeah, and certainly more things like that could be done, but I would offer, Carl, that one thing we did was we had this, we tracked it as the vehicle speed would change. You notice those orange bands change. So we would expect, as we speed up, if there's activity, it would kind of follow there. So we could follow the car body dynamic response with changing speed and still look for where the activity was happening. So we had that covered to a certain point, but I think, yeah, there's certainly more we could do, as you said.
Lewis Leslie Trampler, another excellent performance, Steve, thank you very much. I'm intrigued at the interaction between the track and the vehicle. And one of the thoughts that's gone through my mind, because we know that bogey hunting is speed related as well as track defect related, that if the car body suspension was tuned so that it didn't resonate at the track resonant frequency, would that A, improve the ride quality, and B, reduce the impact of damage on the track?
Certainly would, yes. And we sort of take the suspension as a given, so we don't really, although we know it degrades and we want to account for that as well. But yeah, we don't sort of chase what the suspension is doing so much, although that it could be argued that we should be doing more of that. Yeah, I take that as another example of things we could further look into. So certainly, yeah.
Hi Steve, Ted Sussman at the Volpe Center. This is a great presentation, and I think it's about time we see this sort of a waveform analysis going into our track geometry. We've been seeing it for vehicles for a long time, and seeing it married up with track in the US, I think it is exciting. Can you go to your plot that's the thing of beauty toward the end there?
Oh, yes.
I find beauty in that too, so that's great. At least we have the same sort of appreciation for modern art. But, so, this to me, if I want to correct the 1.5 inch single MCO defect, I know what to do and I know how to make that track last. I know how much of a lift I have to put in depending on the ballast condition to make that last. Right. Now you're trying to fine-tune track with small defects and get it to last. Can you talk about track memory problems with this and how you corrected the track geometry to make sure this, and did this last? Was this a lasting thing?
Yes, thank you for bringing that up, because yes, we did this in 2005, and I looked just before I retired a couple of years ago, so over like 17 or 18 years, it is the same. Track tends to stay where you put it laterally, not always, but better than vertically, right? And that was a lateral correction, and yes, very durable, well, in part because it lowered the wheel rail forces. So that has that benefit too of durability. But the method itself was able to see better the long wavelength deviations. Present, no need to name any. The current tamping equipment does not see longer wavelength than it has to be able to. Right? It's one thing for us to see that it's there, and now the tamping equipment has to see it and remove it. And as I say, that's the part of the challenge we're at right now. So here, we were able to do it because we went beyond what Tamper X was able to do. We took control of the system and said, don't do what you think, do what we say. When we did, the result was beautiful. Use that word again.
I don't want the Tamper to ever do what it wants.
Human control.
Excuse me, and Niall Fagan, and Network Rail. Brilliant presentation, Steve, really enjoyed it. Just, can I ask, did I pick up that last shallow curve? Was the solution to grind the rail as opposed to tamp it? So this is given a wider kind of view rather than just a track geometry that needs tamping.
Yes, grinding in that case was the solution, because yeah, there was really no geometry deviation to speak of. So yeah, that we looked into it further that I'm not showing here, but we did the wheel rail analysis and showed that sure enough, the canonicity does spike, and that explained why you get an evenly distributed acceleration throughout the entire curve. Yeah, it could occur anywhere, but that just hunting just kind of kept on going.
Absolutely. So, I mean, I think that's key, that it's not just one size fits all. It's identifying what the root cause of the problem is and then doing a solution. Just kind of to, just as an aside, West Coast Main Line has Richard Branson's tilting trains as they used to be. Part of the part of the philosophy was we never let the tamper do it at once. It always had to be a full survey first, and then instructed what to do for these long length faults. And incidentally, about 10 years ago, there was a series of bad bumps that were called, which basically train drivers reported as a rough ride. And as Sidson said, the maintenance guys went out to have a look for the fault and couldn't find anything. And what was happening was, it was a feature, I'll call it a feature, a kind of geometrical feature, which caused a response of the body at the bump stops. And it got so bad that, as I said, we couldn't find out what it was, that the managing director of Virgin Trains and the kind of maintenance director were called to the kind of minister, to explain themselves. But we actually found out eventually that it was a feature for a given train. So on this train running at a certain speed, that another train running on the same track, the same speed, didn't see.
Yes. Oh, yes, a great point. Right, and we see the same, it depends on the equipment, as you say, yeah, this is just showing you the response of one vehicle, but yes, we would apply to many others, it would change, and we could adapt to that, so, yeah, I'm glad you brought that point out. So before I end, I do want to mention one person in particular, former British rail researcher, David Marriott, who helped us in this regard, looking at longer wavelengths and correcting them to get the track back to its original lateral alignment and profile.
Hugh Thompson again, FRA. Knowing your co-authors, Mika, Ahmed, and Jim, I know you overlaid GPR survey results on your hot zone, and I'm curious, did you see any sort of track subsurface anomalies in those areas that were perhaps recurrent?
You would think we would have done that, but no, Hugh, we did not. That's the next phase, perhaps. Yeah. That's a good thought, though. Yeah, that should be done.
Brett Story, Southern Methodist University. Terrific presentation. Anytime that convolution and signal processing comes up, I think that's a win for the industry. I think that needs to be kind of commonplace within civil and rail education. We're working on that. It's so intimately tied to mechanics, so I really appreciate that. Can you talk a little bit about, just briefly, the kind of the instrumentation, exactly, what devices were you using to capture this dynamic data?
Oh, so the car body instrumentation was just accelerometers, oriented to pick up lateral and vertical, and mounted on the car body floor over the truck centers, by the way. So yeah, I appreciate the comment about convolution. I'm just a humble civil engineer, but as I got more and more into dynamics, signal processing, I was able to take certain things and run with it, and it was really exciting. Not that I really appreciated I didn't know what I was doing, but I kind of found out as I went, and found out there's an incredible amount of what you can do with that is amazing. Convolution, yeah, not Fourier analysis, but I think I would call convolution a piecewise linear Fourier analysis. So I don't want to claim that I know I can do Fourier analysis. I push the button and the number comes out. But I do want to appreciate the theory too, which I did dive into as well. What is this showing? So.
Okay, Steve, you've done a great job. You've stirred up a lot of discussion, and we really appreciate you giving us the benefit of your 40 years in the industry. So thank you very much, Steve Brisbane.